Hi, this video is going to go over this setup that you have over here, where we have a synth producing a sound going inside of an FPAA, where we're going to have a low pass filter that we're going to reconfigure that FPAA dynamically. And to do that, we have a graphical user interface that has ability to receive Midi values from a Midi controller, control these knobs, and then send UART commands to an Arduino Uno R4 that then parses that data and reconfigures the FPAA dynamically on the fly and controls the cutoff frequency, the gain, and the quality factor. To achieve that, we are going to use this algorithm method, and we're going to use the OTC2312 Arduino Uno shield. And for more information about the pinouts or anything else that I don't address in this video, you can go to Okika's website and download the datasheet of this board. Alright, so this board is originally designed to interface an Arduino Uno, and on this video I'm going to show how you can use to interface an Arduino Uno R4. Same pinout, just a different microcontroller, and it just shows the capabilities of the OTC2312 in interfacing different types of Arduino Uno flavors. Okay, so let's go over the hardware setup, and before you connect anything to the OTC2312, it's important to see the levels of voltages coming out of the hardware that you're using, or the sensors, or any type of system that it's interfacing with the OTC2312. I have here the output of the synth. I'm going to connect these to the sound card. Let's just see if it's working for now. We have sound coming out, and let's connect these now. I have a board here to have access to the right, left channel and ground, and let's connect that to an analog discovery. Connect that to channel number 1. I have already the grounds connected, and let's go over the software. I have Waveforms here, and I'm going to open the scope, press play, and let's run here the sound, and you can see already the waveform. And this is probably the levels that I'm going to take, that I'm going to have for the rest of the demo. So you can see that it's fairly small and manageable. So let's go to measures and get some values out of these. Alright, minimum, maximum, and average. So it's below 1 volt peak to peak. So just for the sake of demonstration, I'm going to increase the volume so you can see these coming out. Alright, so even going all the way up, this is still a safe value to put inside of the OTC2312, as long as you feed the signal, these negative to positive voltages, into the single end inputs of the OTC2312. Be careful, do not feed these into the differential pins, because otherwise you will damage the FPAA. Okay, so everything is working. Now let's finish connecting the rest of the hardware. Turn off here the volume. Alright, so we have here the 2 Arduinos. I'm going to put the Uno on the side, and I'm going to use the R4. I have the OTC. Let's connect these to the Arduino and power it up. Okay, and the first thing that I'm going to do is connect reference points, the ground. Alright, then the output of the synth, instead of connecting to the oscilloscope, connects to IO cell 1, the single end pin. Alright, and we connect IO cell 5 after the op amps that are converting differential to single into our board. And then from here, connect to the sound card. Alright, cool. So everything is connected. So let's go back to the software. We don't need waveforms anymore, and let's go over an example of a programming example. Alright, so for these, let me just show you here what we're going to do. The first thing that I'm going to do is just a bypass using state-driven. I'm not going to explain in depth in this video how to use the state-driven. You have another video that you can follow with that information. we're just going to program the first one, bypass. So how do we do that? Go to our Anadigm. We have here our cab. Press the IO cell that you want. In this case, I want IO cell 1. Double click, input, amplifier. So here I have already the resistors on the PCB boards that interface with this operational amplifier to do our Rauch filters to convert single-ended to differential. Inside of the cab, everything is a differential signal. And IOCell 5 set up as an output, bypass, and then connect these over there. Here you go. Alright, so let's program these. We're using the state-driven method. Alright, transitions, I'm going to pick up FPAA as the primary state generation, and I'm going to generate a file that contains, let's put here, that contains the configuration of the FPAA into bypass mode. I'm going to copy that. I'm going to open the code that interfaces the Arduino using the state-driven. Going to that .h file, and we're going to paste that over here. Alright, so let me turn on the Arduino and let's program these. Alright, and the first thing that we're going to test is if the sound coming out of the synth passes through the FPAA as a bypass and comes to our sound card. So let me do that, press play, control the volume. Alright, we're good. So we have the sound passing through the FPAA as a bypass. Okay, so what if now I want to implement a filter, a low pass filter, and I want to control dynamically or in real time the cutoff, gain, and quality factor. So this is where we're going to use the algorithm method, the other way of programming the FPAA. And before we go and I show that, let me just talk about the files that we need. Anadigm designer in algorithm method is going to generate 4 files. That's the API code. And you don't mess up with any of these files. You just copy and paste them into your project where you want to use this. And then all your code is going to be done under your project file, in this case this Arduino file. This is a very clean way of doing code. They have this set of files that manipulate data structures in memory, and then the user is responsible to create code that interfaces with or read from those pointers, from those data structures, and then sends the data over SPI to the FPAA. So very, very straightforward to use this. So let's go to the software and show how that is done. Alright, we're going to open our Anadigm designer, and in this time, instead of a bypass, we're going to do right click, cam. We have a bunch of cams here, so I'm doing the low pass example using a bike quad. Let's create the cam, put it inside. Alright, I'm not going to cover these parameters or options. We can do another video to talk about these. And these parameters here, the frequency, gain, and quality factor, is what I want to control in real time. Just pay attention here that so this cam is working at a certain frequency right now, running at 4 megahertz, and if I pick a different clock, you can see that these parameters change. So I want to control, let's say, from 0.2 to 10 kilohertz. So right now there is no clock available to achieve those parameters. So how do we change the clock so we can have access to different values? So if you go to your cab and you double click, you have access to 2 main clocks. I am going to play with the second clock and make it at around 1 megahertz. And then here we have the clocks available on the cams, and I'm going to say that clock 0 is going to use that 1 megahertz, and let's divide that by 10 so we can have access to a 100 kilohertz clock. Press OK, double click on the cam, and now I have my 100 kilohertz, and you can see here that I have the bandwidth that I'm interested in using. This particular cam, if you go here on the button that says C code, is going to have available these 2 functions into the API code. A low pass filter where you control the frequency, gain, and quality factor, and a low pass filter where you control directly the capacitor values of the switching capacitors. Okay, so let's finish this setup. Connect these here, connect these here. We are good. And we have these here ready for us to see what's going to be generated. And I'm going now to generate the algorithm method. So pressing that. These are the 4 files that are going to be generated under where your project file is created or saved. Under cam functions, I have the ability to select which functions do I want the API to have. So I'm going to have all of these for now. And generate options, you have additional configuration values that I'm going to leave them as default for now. And I'm going to press generate and update the folder F5, and you can see here the 4 files, the 4 API files. So I'm going to copy them inside of my project folder, and I'm going to open that project. And you can see here that all you need to do is to call the API header files to have access to the functions and those data structures. Not for sake of time, I'm not going to explain the code here, but pretty much what it's doing is calling those functions of that API, read memory positions, and then using the SPI to send the values to the FPAA. And the while loop reads a UART, reads UART data, parses that data, and then sets the frequency, gain, and quality factor accordingly. Okay, so we have pretty much everything. I am going to program our Arduino, so let's do that. All right. That's it. I'll go here on the hardware, and I'm going to turn it on, and hopefully we can hear the same sound. So it's a little bit more muffled because the filter is already working. I don't have a way to control the filter right now. So let's go to this code in VSCode that I have here. It's a Python code that reads Midi and then sends you our data. Let's run these. Just thanks for your patience here. Alright, and I have here a Midi controller. Let me just put it on the camera so you can see what's going on. And I'm going to connect to the Arduino and connect also to the controller, so I have the ability to control knobs over here. Okay, and let's press play and see if it works. Go and play with other cams and have fun.